Inertial guidance is a subject that has been much in the technical news and also in the general discussion of scientific, political, and social advances here recently. We know that inertial guidance has received quite a lot of publicity in connection with various military weapons, the new ones. The Atlas, the Titan, Jupiter, Polaris, and for the weapons that are still to come, inertial guidance will be one of the important factors. Today, my purpose is to discuss the reasons behind this recent interest in a subject that is, after all, very old so far as the theory is concerned, but one that has been given support in copious amounts only recently. The basic problem that has to be handled in all these missiles that we have today is that of guiding the missile from where it starts to some place where it can accomplish its mission. Now, this is the real part of the job that I am to be concerned with now. The missiles are all kept under control, that is, kept flying under conditions where velocity in direction and magnitude is adjusted so that the missile accomplishes its purpose. This is done, this kind of thing is done by what you might call extensions of the common autopilot that has been in use in airplanes for a long time. This control is concerned with stabilizing the missile and keeping the missile system so it can receive commands as to what should be done with this velocity of the missile. Guidance deals entirely with the commands that should be issued to the missile to change its velocity so that it accomplishes the purpose. Now, guidance as such is a very, very old art. People who walked from one place to another or who rode in dugout canoes had the problems of guidance. Some destination was in mind, and some means of traveling had to be present. It might be just a man's own feet, it might be a horse, it might be a log, it might be a sailboat. But he had, in some fashion, to judge whether the motion of his vehicle or himself was the kind of motion that would accomplish the purpose he wished to accomplish. And he had, therefore, to guide himself and his vehicle in some way. Originally, he merely did this by looking at the destination and changing his direction of motion so that he would reach this destination. When he could no longer see the destination because of terrain, he picked up some landmark that was not the destination but had some relationship to the destination from his past experience. And he could guide himself by visual observations of landmarks on the surface of the earth. This art, of course, is practiced today. Anybody that walks across a field uses this kind of guidance. Anybody that sails a boat along a coast uses this kind of guidance. The troubles that develop, of course, are obvious. In bad weather, in night, under wrong conditions of terrain, you can't use this visual contact guidance even if landmarks are available. So that man, in his advancements with technology, developed means to completely overcome these guidance problems with terrestrial landmarks. The radio and radar of today do, in fact, provide contacts, radiation contacts, no longer visual contacts, but radiation contacts with terrestrial landmarks in such a fashion that weather, distance, terrain, and the things that used to completely blank out this visual contact guidance, all these things are no longer problems. The situation, however, is complicated by the fact that you replace mountains and trees and terrain features as landmarks. You replace these things, these natural things, by artificial things, radio stations, radar reflectors, and things of this nature. And all of these systems imply cooperation from somebody not in the moving vehicle, or radiation artificially generated by the moving vehicle. So that in spite of the excellence of this terrestrial landmark type of guidance, the result is not satisfactory for any situation such as we have in a submarine, where you cannot have radiation contact of this kind, or where you're flying over enemy territories and the enemy will not cooperate with you. These difficulties are partially overcome by another method of guidance, which is very common and which is also very old. This method is basically the use of landmarks with visual contact, but landmarks not on the earth, but landmarks in the sky, that is, celestial landmarks. And this whole game that started with the shepherds who looked at the stars and observed that there was a pattern that could be recognized and changed so slowly that it could be used for landmark purposes. This was the start of celestial navigation, the use of stars for navigational purposes. With the years, methods improved, instruments improved, knowledge improved, so that by looking at these landmarks in the sky, you could set up a whole celestial sphere. This was the surface, a space, if you like, in the sky, which had certain definite geometrical properties, and these properties could be used for the purpose of locating points on the Earth's surface without having to depend on radiation contacts of any kind with some terrestrial object. And this celestial navigation is an art that has been in a very good state for many years. As a matter of fact, in the last century, the instruments and knowledge were brought to a state where, for many purposes, the celestial navigation is quite satisfactory. Now, this method, which is in a great many cases useful, well beyond what you can do with terrestrial landmarks, this method is not good when you try to navigate a submarine under the water and without looking out, without putting up a periscope or any other means for observing the stars. It is also not good when you are in regions of the Earth's surface where you can't depend on having weather through which you can observe the stars. There is some hope in this direction because recently, as we know, people have been making observations on celestial bodies not with visual light, but with radio waves of various wavelengths. This is a hope, but it involves equipment that is quite large and cumbersome compared to what you would like to carry with you in many cases. And this is the development of the last 15 years, when there have appeared overpowering reasons for making self-contained guidance systems. By self-contained, I mean systems that do not require any external assistance or have to generate any radiation that must go out from the vehicle to external objects. The military requirements, of course, started this. The bombers that had to go over enemy territory, the submarines that had to remain submerged for a long time with an accurate knowledge of position, the ballistic missiles that had to go for long distances without guidance along the way. All of these things led to a whole series of developments that have actually, after a rather slow start in about 1945, have actually now got to a point where, if we use the popular word explosive, I think we would be at least as right as a good many people are when they use the same word. Now, in all of this, we are not concerned with any new principles. There are no new particles that have had to be discovered. There are no new ideas of physics. There are no new mathematical techniques that we've needed. The theory is completely and entirely covered by Newton's laws of mechanics. And these laws of mechanics are the same now as they were a century or so ago. The only thing that has occurred belongs in the realm of modern technology, which has, as a result of many, many developments, become able to produce performance of components and systems orders of magnitude better than the performance that we could have realized, say, 20 years ago. This all started with electronics, and this a subject that has become known as automatic control, of which several mechanisms is one section. All of this technology has become available, and from this technology, we are now able to do things that were unthinkable, say, 25 years ago. The theory had been worked out. The theory is old, at least 40 years old, and in its beginnings, older than that, 50 or 60 years old. The names are in the book. One of the prominent names is that of Professor Schuller of Germany, who did his work in the early 20s. That is, he did his writing in the early 20s, and the beginnings were associated with the so-called marine gyro compass. Now, the ideas that are involved in inertial guidance to make completely self-contained systems are very simple. The basic idea is that you can replace a celestial space that provides the landmark for celestial navigation. You can replace this space with a system, a mechanical system that is of reasonable size and can be carried within a working guidance system on board vehicles that are of reasonable size. Without becoming specific about the size matter, I can remark that from 15 years ago, when we first began to get indications that inertial guidance would be possible, we were talking about systems that in their entirety on the weight and balance chart of airplanes were in the vicinity of 2 tons, 4,000 pounds. And without revealing any classified material, I can say that today the systems that are being used and being contemplated are systems whose weights are not 4,000 pounds, but somewhere around 1 or 2% of this 4,000 pounds. This is progress of, say, 10 years. And the end is not yet. We still have to make this equipment cheaper than it is now, but I am sure that as time goes along, you will find inertial guidance equipment not in the advanced military weapons, but you will find it in commercial vehicles, on the land, in the sea, in the air, and in space, and you will find it in any reasonably large, say, private vehicle. Of this I am sure, and I'm also, I believe, on firm grounds if I say that 10 years from today, inertial guidance will be such an ordinary thing that it will not be even remarked by the people who are using it. The only problem will be to get the cheapest system from the manufacturer that can supply it. Now, I would like to outline the background of this game of inertial guidance for the purpose of indicating the kind of problems that are involved and why I think that we can expect the type of developments that I have outlined. Actually, inertial guidance started a long time ago in its embryonic beginning, because the gyro compass was a device which did, on the Earth's surface, pick out a direction associated with north by detecting, if you want to call it that, the Earth's axis of rotation and the direction of this axis. The gyro compass was in use in World War I, as we all know. After World War I, gyroscopic instruments became used in aircraft along about 1918 for determining direction and amount of turn. We had the so-called turn indicator, which was commercially available actually in the early 1920s. The Sperry Gyroscope Company and the Pioneer Instrument Company could supply this equipment to you. In the tail end of the 20s, General Jimmy Doolittle, General Ben Kelsey, and their colleagues did, in the so-called Guggenheim competition for blind flying, successfully use gyroscopic instruments for direction indicating purposes. Here you did not indicate motion over the ground, but you indicated directions with respect to the Earth by means of gyroscopic equipment that did not require any continuous contact with the outside world. The instruments that they developed and the ones that had been previously available are in all airplanes of any pretension to blind flying capabilities today and will probably be for a long time. The inertial guidance end of this thing uses the same principles that were used in those instruments of universal application, except that instead of merely giving the direction of the vertical and the direction of north or some other reference direction, that you, in effect, indicate the distance that you have moved along some known path towards some destination. The direction indicating properties of the equipment still has to be there. You still have to know which way is up and which way is north, or some equivalent set of directions. You still have to know that. This is the basic property, one of the basic properties of the equipment. In addition, you have begun to indicate distance along a path by adding to these direction-holding gyros the means for integration of motion, integration of acceleration. In other words, you measure the resultant of gravity and acceleration, and by a computing process have translated the summing up of those bits of acceleration first into velocity and then into distance. So that the inertial guidance philosophy and the equipment that's associated with it are really not new things. They're merely developments of old art with refinements that are made possible by the developments of modern technology. Now, in order to make these words a little more definite, I have some charts here. Now, these charts are taken from this little book. I'm not trying to sell the book. It's entitled Inertial Guidance, and I'm one of the co-authors. The reason I'm using these charts is that I save a lot of time over and beyond the time I'd have to put in if I tried to draw the same thing on the blackboard. This first chart is intended to represent schematically the Earth here and the celestial sphere as established by points associated with stars out in space. The 6 stars. We have a celestial pole and we have a celestial equator. And then there's certain coordinates like the meridian of the vernal equinox and the distance up from the celestial equator to establish points on the celestial sphere. Then down here on the Earth, if you establish the point on the celestial sphere just above the point on the Earth, you have the essential information by means of which you can find your position on the Earth in terms of observations of the celestial sphere and, of course, a knowledge of the rotation of the Earth. This celestial sphere works fine when you can see it. When you can't see it because you do not wish to carry the equipment for that purpose, or because it's obscured for some reason, you can replace the celestial sphere by an inertial reference package carried down inside of equipment on board the vehicle that you wish to guide. This package contains some type of gyroscopic arrangement. Now, these gyros may be 2-degree of freedom gyros, so-called, that is, gyros that can move in any fashion whatsoever as far as orientation is concerned with respect to the base, or single-degree of freedom gyros of such a nature that they will operate only about a single axis. This model over here is a schematic device with a wheel and a pointer that illustrates what is inside of each one of the single degree of freedom gyros if you mechanize in that fashion. A spinning wheel which holds its orientation unless a torque is placed upon it with respect to inertial space, and inertial space is the same as the stars. That wheel and the mechanism associated with it will indicate if this structure to which the base of the gyroscopic device is mounted will indicate whether this base in here has changed its orientation with respect to the stars. And if it has, there is in practice a series of gimbals, a system of gimbals with motor drives that, taking signals from the gyros, will cause this thing to come back to the orientation in which it was initially placed among the stars. With sufficient sufficiently high-quality gyros in here and a proper drive system, this device can be made to hold its orientation among the stars with quite good accuracy for quite a reasonable string of hours. Now, what do we mean by reasonable accuracy? We can get at this roughly by considering that the Earth, being a sphere of some 4,000 miles radius, will have out here on the Earth's surface a distance of about 1 mile corresponding to an angle of 1 minute of arc. So that if you are interested in inertial guidance to a fraction of a mile, you must have these gyros maintain their orientation to better than a fraction, to some reasonable fraction of a minute of arc over the time period that you wish to use it. In effect, with units of that high quality, this inertial reference package stands still down inside of the equipment and will provide exactly the same information as that sphere out with the stars provided in the preceding chart. And you can use that as a reference against which you can guide, the same way that you guide in celestial guidance. Now, if this package remains stationary among the stars as far as its angles are concerned, and you line this axis here up parallel to the Earth's axis of rotation, and then between this inertial reference package, which is held still by the gyro signals and the servo motors coupled with their electronics, if you provide a clock-driven motor here, driven with sidereal time, so that this gimbal is forced to rotate, no servo here, merely time, that this gimbal is forced to rotate with respect to this inertial reference package, this gimbal then stays with some meridian on the Earth. And so this gimbal then becomes, for the purpose of guidance, an Earth reference gimbal against which you can determine your position on the Earth's surface. Now, this is the essential idea of inertial guidance. The problem is to get a sufficiently good set of gyros and servo mechanisms for this inertial reference member. Now, looking a little bit more closely at the mechanization, we can place 3 gyros here, each gyro picking up an angular deviation about one axis. This one might be about this axis, this one about this axis, and the other one about an axis at right angles. These 3 gyros, single degree of freedom now, or you would use two degree of freedom gyros here, pick up the angular deviations, generate signals which come out into some kind of an electronic box that supplies power to the servo drive in such a fashion that no matter how this base here that carries this thing is moved, this package inside holds its orientation with respect to inertial space. This is the basic idea behind all inertial guidance as far as the geometry of a coordinate system is concerned. Please notice that the gyro itself is not an intelligent piece of equipment. It's on the moronic level, if you want to call it that. A good one will supply signals that will maintain itself in the fixed orientation, but that fixed orientation must be supplied to it before the system is put into operation or is started on its job. No gyro is completely perfect, although we are now getting gyros in which we can talk about perfection that represents fractions of a thousandth of Earth's rate. Earth's rate is 15 degrees an hour, or 900 minutes an hour. A thousandth of Earth's rate is roughly 1 minute an hour. And so if I'm talking about a rate of a thousandth of Earth's rate, and a fraction of that, I'm talking about a fraction of a minute of deviation per hour, and ordinarily we refer to this imperfection of a gyro as drift. Now, by this scheme, we can then establish physically a set of coordinates on board a craft that has the property of giving us something against which we can measure directions for guidance purposes. Now, in order to use this set of coordinates that we've established by the gyros, we must in some fashion translate the indications that we can generate on board, translate those indications into distance moved along a path. And the principle we have available here is the same one that's used in the gyro, where we take advantage of the properties of a rigid body formed as a rotor. The same property of mechanics that is stated and covered by Newton's laws can be used to indicate acceleration, and acceleration with respect to inertial space. Many mechanizations of the inertial guidance principles are possible, and not only possible, but at the present time brought into existence by various manufacturers and many agencies. In my opinion, the next few years, 5 to 10 years, will indeed demonstrate that not all of these are equally useful and effective. And this means that just as we now have in automobile engines one fairly common design of the piston and crankshaft arrangement, that in the future we will not have more than a very few kinds of inertial guidance equipment. The principles are always the same. The mechanization depends to some extent on the job that has to be done. Here I show an indication of the first and simplest type of mechanism. You have a package. Many people call this a platform. I don't happen to call it a platform because it's not a platform. It doesn't look like one. It looks more like a pineapple. But this platform contains the accelerometers and the gyros all connected rigidly to the same members. The gyros, working through some electronics out here and these motors, maintain the orientation of this package wherever it is placed initially with respect to the stars, inertial space. The accelerometers measure acceleration along each of 3 axes fixed with respect to that package, and ordinarily provide an integral of that acceleration as the indication. Nowadays, the indications come out from these units already resolved and already in the form of pulses suitable for use in some digital computing system that is connected as part of the system. The result of these signals processed by the digital computer, which compares the results of this computation with some stored information that was put in the computer initially to give the desired guidance track, the discrepancy between what comes out of these instruments and the computer with what we should have gives then a command signal which can be sent to the missile and the missile control system to cause the missile to come over and correct itself so that it accomplishes its mission. This is the essence of guidance. A system like this disregards, if you want to call it that, the direction of gravity as far as the stuff inside of the package is concerned. Gravity, of course, provides part of the input to these accelerometers, because no accelerometer measures acceleration only if gravitational fields are present. But the computer and the mechanization is able to distinguish between what is a pure acceleration effect that you wish to integrate twice to get distance and the effects of gravity. So a system like this with a gimbal arrangement that permits 2 degrees of freedom of this with respect to the base, so actually 3 degrees of freedom of this with respect to the base, is typical of what's used in ballistic missiles. Now, if you're going to do navigation over the Earth's surface, the essential property that's associated with the Earth that you use for this navigation is the direction of the gravitational vector, because the direction of the gravitational vector gives you the normal to the Earth's surface, the idealized Earth's surface at that point. And by comparing the direction of this gravitational vector with some directions in the geometry that was set up to relate the equipment and its reference directions to the celestial sphere, the comparison of those 2 angles gives you position on the Earth's surface, when, of course, you correct for the rotation of the Earth, as you can do by chronometer. This is exactly the process you use in celestial navigation. The essential piece of information over and beyond this set of inertial coordinates that you have associated with your inertial reference gyro package, the essential information is the direction of gravity. And one way that this can be achieved is to make up an equivalent pendulum system. You can put a couple of specific force receivers on a package, and specific force is the resultant of gravitational force and the lagging behind effect, the force associated with the lagging behind effect when you accelerate a particle in the world in which we live. You can, in effect, put 2 pendulums here, and these pendula provide signals out here to some signal generator system that supplies torques on these gimbals so that this structure in here is kept lined up with the direction of gravity no matter how the base is tilted. The reason for not using a simple pendulum is very obvious to anybody who has tried to find the direction of gravity on an airplane by hanging a string and a weight system up. As the airplane gets small accelerations, the bob on the end of the pendulum string goes all over the place. And since you must have angular information to a fraction of a minute of arc, this is not satisfactory for guidance purposes. But you can, by using these pendula here and this servo system and the electronics, you can cause this thing to be an equivalent pendulum tuned to have a period which causes this to tip in angle at a rate which is proportional to the linear acceleration divided by the radius of the Earth. If that is true, then this indication of the vertical remains correct no matter how the base is moved. Dynamics of that kind can be put in electronically. It's very difficult to do it mechanically. This is equivalent to what they call Schuller tuning. Now, to talk about an explicit system, this is the Earth, this is a path on the Earth's surface. You can have a set of gyros that hold a direction in space. You can have a platform that holds the local vertical. As you move over the Earth's surface, this collection of gyros maintains a position in inertial space. You can correct out, of course, the effect of Earth's rotation by a drive, a sidereal time drive I indicated before. And if you have a local vertical package that remains along the local vertical, if you measure the angle of this little local vertical package with respect to this gyro inertial reference package, that angle then gives you the distance you've traveled over the Earth's surface. Now, a mechanization that has worked out along those lines is shown here. Inertial reference package, sidereal time drive, a gimbal that you can set up to establish this direction here, normal to any great circle that you wish to fly, and then these base motion isolation gimbals with a little pendulum package out here that has Schuler tuning, and so you measure the angle between this little fellow and the gimbal in which it sits, and that gives you the distance along the Earth's surface. You then can, in the computer, put in a degree of freedom so that you can move for some thousands of miles on either side of this. This is the essence of the so-called SPIRE system that was built and tested successfully some years ago. Now, another mechanization that is widely used uses a gyro package and a specific force receiver package mechanically connected one to the other in such a fashion that the signals from the specific force receiving package are used to cause the gyros to tilt, if you like that word, so that the gyro axis remains in a fixed orientation with respect to the local vertical. This can be Schuler tuned in accordance with the principle we noted a minute ago. Now, in this case, the signals that have to be sent to the gyros in order to cause them to tilt properly, these signals, corrected for the Earth's rotation, can then be processed in a computer, not shown here, in such a fashion that the initial position in inertial space of this gyro package is not maintained physically, but is remembered in the storage of a digital computer. And then as this thing moves along, the answer to the inertial guidance problem comes out from the computer, not from geometry in the gimbal. This principle is particularly well suited for navigation over the Earth's surface. The others may be used over the Earth's surface or out in space also. Now, these ideas that we've discussed for inertial navigation, I am sure will receive many applications in the future. They will be widely used. I would almost say that in vehicles of any pretension, they will be universally used. And the developments that will appear will be in the direction not of new principles, but of improvements in mechanization, greater performance, cheaper prices, and smaller weight. The thought that I have is that within the next 10 to 20 years, inertial guidance will be so universally used that it will not be the subject of any lectures such as we have given here today. Thank you very much.